Hi, in this lesson I'm going to look at three example word problems that are applications of rational expressions used in equations. They're going to be number problems, motion problems, and mixture problems. So I'll do an example of each one. First problem is posed right here. A number is half more than 3 times its reciprocal. Find the number. For starters, let's define a variable. So we'll say, let the number equal n. Try to choose a variable that connects to the situation, n for number in this case. Now, we want to translate the English sentence into a math sentence. Is means equals. It says a number. So we get is covered, we've got number covered. Now, half more than means to add half. 3 times and reciprocal. Reciprocal means 1 over the number. Okay, there we go. So let's read it again. A number, there we are, is, yes, half more than 3 times its reciprocal. Okay, that's the trickiest part of these problems, is translating the English into an effective math equation that's equivalent. What we're going to do now is the same as what we've done with other rational equations. We will find the LCD, 2n, and we'll multiply by it. So term by term, I will multiply by that result of 2n. I'm just going to show that nice and clearly for you. There's my 2n multiplied into each term. Now, I'll multiply out, and I'll cancel common factors where possible, and you'll see I'm left with a quadratic equation. I'll gather everything to one side, and I will factor this, if possible, and typically they will factor, they will work the numbers out that they're kind of convenient. This works out to 2n plus 3 and n minus 2, leading to the results of negative 3 over 2 or 2. Now we just need to verify that these results make sense. Negative 3 halves for a number, certainly that's possible. It's possible for numbers to be negative, possible for them to be fractions. 2 as a number, that's also possible. As well, you can actually follow these numbers through the description to make sure that they're equivalent in terms of the original equation by substitution. I'll leave that for you to do. But here's your result for the first example. Here's another example. A motion problem. Now, in these problems, you're going to have distance, velocity or speed, and time. And the relationship is v equals d over t, which can be rewritten in different ways. Now, I like to solve these problems by making a little table. We see that we have a description of 2 scenarios here, and you may want to pause the video and just read it over for a bit before you carry on. But we have a normal scenario for a train and a day where it's late that's being compared. So if we set it up a little table, we can refer to a normal day and a late day. Then we can list the distance traveled, the velocity or speed, and the time taken. Now we're told that it's 140 miles each time. That doesn't change. And we have a comparison here. On the day that it goes late, it goes 5 miles an hour faster than usual. So if I refer to the normal day as v, then the late day would be v plus 5. Now I'm also told something about time. It says that one day it leaves a half an hour late. So compared again to the normal time, which we could just call t, half an hour late and arriving at the same time requires a shorter time. So t minus 0.5. Okay? I'm just going to make a note there. It's because it's less time because it's late. So from that we can form an equation here. And we can say the late time is equal to the normal time minus half an hour, which is basically summarizing that third column. Now let's use this knowledge about the relation of velocity, distance, time, and we'll rewrite time as distance divided by velocity. So I'm using subscripts to separate the distances as being late distance, late velocity, normal velocity. Okay, because there are differences. We don't want to just use d and v, which would assume that everything's the same. Now, let's substitute what we know. I know in this case that this distance is 140. The late velocity was called v plus 5. I know that the normal distance is 140, and the normal velocity was just being called v. All right. At this point, you now have an equation that has only one variable. This is really the goal of these scenarios, is to produce an equation with one variable. Here's your LCD. We'll multiply by it. Now, I'm just going to write the result over here. Maybe you should pause at this moment and just try to get a result yourself and then compare it to mine and rejoin me. Okay, here's the fully worked solution for you to compare to. The LCD of 2, v, and v plus 5, three factors, two monomials and one binomial factor, are multiplied onto all three terms. In the first case, v plus 5 is going to cancel with this v plus 5, leaving 140 and 2v. In the next case, the v factors will cancel, leaving this result. And in the third case, the 2's will cancel, leaving this result. On the next line, I've expanded them all, canceled out a common term, gathered everything to one side, and again I have a quadratic equation which I'll factor, producing two roots. And in this case, I'm going to reject one answer because this velocity of negative 40 isn't logical or makes sense in this situation, but 35 is. So what we find out is that the normal speed of a normal day is 35 miles an hour, and on the fast day then it goes 35 plus 5, or 40 miles an hour. So that's a typical motion or kinematics problem. Let's move on to the third type, which is a mixture problem. Sometimes these are called work problems. You may want to pause and read the question a few times. What I'd like to do, similarly to last time, is make a table that summarizes things. So have a look at the information and try that, then rejoin me. Okay, here's the information laid out in a chart. I've got Mr. Jenkins and his son, and I also described together. Now there's two components to this one, a little different than the last problem. We've got the time that it takes for each one to do a job, and it says that Jenkins can do the job in an hour less than his son. So the son is the reference. Let's make that the variable t for time. Jenkins then is one less. We're also told together what the time takes for them to do the job. Now, what we want to do with mixture and rate problems is we want to think about rates of doing the work or the jobs or what have you. Sometimes it's filling a container. Okay. Now the rate is the reciprocal of the time. So what this is saying is 1 over t minus 1 is how quickly that Jenkins on his own can do a job based on time. The son, 1 over t, and together 3 over 2, or 1.5 jobs can get accomplished in an hour. Think about it. If a job can be done in 2/3 of an hour, like 40 minutes, that leaves 20 minutes, which is half again the time. So half again of a job could be done, or 3/2 of a job, 1.5 jobs. So from this, we're going to form this equation. We're going to say the rate at which Jenkins works and the rate at which his son works is equal to the rate at which the two of them together would work. And similarly to before now, we will have common factors on the denominator, LCD, that we multiply by. This is going to produce a 2t and a 2 bracket t minus 1 and a 3t bracket t minus 1. So I have 4t on the left minus 2. I've got 3t squared minus 3t on the right. Again, I have a quadratic. Gather everything to one side. That 4 becomes a minus 4, gathered together. Try to factor this. Again, typically these are going to factor. There's going to be two negatives here, 1 and a 2, leading to a t equals 1/3 or t equals 2. Now, let's interpret the results and make sure they make sense. If the time is 1/3 of an hour for his son to do a job, there's a problem, because it says Mr. Jenkins takes an hour less. 1/3 minus 1 means he takes a negative amount of time. So I need to reject that solution and I need to look at the 2. Solution. If the son takes 2 hours to do a job, his father takes 1 hour to do the job. That's reasonable and logical, at least. Also, if I put that into the rate parts, what we're finding is that the rate of doing a job for the son is 1/2, or half of a job per hour. Okay? And the rate for the father is 1/2 minus 1, or 1, meaning the father can do the entire job in 1 hour. So taken together, this makes sense then that it would take less than an hour, or 2/3 of an hour specifically, to do the job. So those are 3 helpful examples for you, hopefully, to get a sense of how to work these problems, take the information, lay it out effectively using some relevant variables. And with practice, you will get better and better at this. I wish you much success doing these problems.